Double-slit experiment. Wave-particle duality. How can something that we perceive to be a particle can itself also have wave properties? The double-slit experiment is often used to illustrate this non-intuitive dual property of atomic and subatomic particles. Start with an atomic or a subatomic particle. Next, throw this particle in the direction of these two slits. Then observe the landing location of the particle once it reaches the back wall. This is the front view of this double-slit experiment. Let's see this double-slit experiment in action, from the side view. Throw a few electrons. Finally, let's finish this double-slit experiment by observing the back wall. It is common to plot the intensities of these fringes on a graph, so that their characteristics can be analyzed. You may have seen a similar graph prior to watching this video illustrating that these peaks represents the intensities of the fringes above. In contrast, you are unlikely to have previously heard an explanation as to why these gradually increasing valleys exist. Similar peaks and valleys can be seen between two separate graphs by two independent teams of scientists that performed the double-slit experiment. One team used 60 carbon atoms in 2003, while the other team used electrons in 2012. What is causing these valleys to gradually rise? Whoa! Is the particle really being guided by its wave? How can the double-slit experiment be used to show this wave-particle duality? To answer this, we will make three simple adjustments to the double-slit experiment. These adjustments theoretically impact the wave as it evolves through time. And since the wave guides the particle, we end up theoretically impacting the particle's location. As a particle passes through one of the two slits, the particle resides in one of these 18 distinctive locations. The number within each location indicates the probability of the particle residing in that particular location. When the evolving wave reaches the third critical separation distance, the separation distance, identified with capital D, is as follows. As a result, the diagonal distance, within each of these two sets of diagonal probability locations, is momentarily shortened, as seen in blue. This causes the particle to momentarily reside between one of these two sets of diagonal probability locations. This leads to particles being present in the two semi-empty columns in this time-elapsed double-slit experiment back wall, as identified by the two red arrows. This in turn is what causes these initial gradual rise in the valleys, as identified by the two red arrows. As the wave continued to evolve and reach the second critical separation distance, distance D now becomes the following. Shortened diagonal distances between each of these four diagonal probability locations can be seen in blue. As a result, the particle momentarily reside between one of these four sets of diagonal probability locations, leading to particles being present in these two semi-empty columns. And finally, these raised valleys. As the wave continued to evolve and reach the first critical separation distance, distance D now becomes the following. Shortened diagonal distances between each of these six diagonal probability locations can be seen in blue. As a result, the particle momentarily reside between one of these six sets of diagonal probability locations, leading to particles being present in these two semi-empty columns. And lastly, these raised valleys. You may have noticed that, in the double-slit experiment graph for electrons, the difference in height between each set of gradual increasing valleys are fairly consistent. These bottom sets of valleys are due to these two momentary residents of electrons. These middle sets of valleys are due to these four momentary residents of electrons. These top sets of valleys are due to these 6 momentary residence of electrons. As a wrap-up, this consistent increase from 1 electron residence on either side, to 2 electron residence on either side, to 3 electron residence on either side, correlates with these 3 consistent increasing sets of valleys in red. Thank you for watching. I hope you've enjoyed this video and look forward to seeing you in the next video.